introduction. I'm from Howard, and I'm going to talk about challenges in high-dimensional variable selection today. This will motivate Lucas's talk about model X knockoffs. So today's talk, we first introduce why we care about variable selection. So basically start with some motivating applications. And then we define a statistical question, which is how do we do variable selection in a statistical framework, and how do we make guarantees on the results that we have. And then we're going to review some existing methods and talk about their pros and cons. Okay, so nowadays, we get a lot of questions in science that involves big data. So for example, if you are a biologist, you care about the expressions of which genes contribute to a certain disease. Or if you do GWAS, you're going to ask the question that which SNPs are causal for a certain trait. And we recently got this problem that for a protein, some residues are more essential for the stability of the protein than the others, and you want to learn which one of them is actually essential. And also, in EMRs, some parts are just more relevant for diagnosis, and you want to identify those parts. And if you're a social scientist, you might care about what socioeconomic or demographic variables can affect future outcomes. Yeah.
Can you give us an example of the order of, you're saying big data, but like I'm not familiar with the residues of a protein, like how many residues, how big is the data for each one of these?
Yeah, so they have different dimensions. That's a very good question. For residues, the protein, I think a protein has like 100 to 100 residues. For the others, they might vary. So genes could be in the thousands or even millions. They have different dimensions. Is that what?
So anywhere from dozens to millions.
Yeah, so basically very, very large number of them. So the statistical setup would be we have a variable y, we call this the outcome or the response, and we have x, which is random, which is a vector. We call them potential explanatory variables. Someone call them features or covariates. They mean the same thing. And n, the sample size. So in order to do inference, we gotta have some samples, and n is our sample size. And p, of course, is the dimension of the potential explanatory variables, which is what Alex just asked. And of course, there's a lot of times that n is much smaller than p, and that's where the challenge comes from, actually. And our question is, what is the conditional distribution of y given x? So we use f subscript y given x to denote that. And of course, without any extra assumptions, this is only possible if we have an impossibly large sample size, and that's going to be exponentially in p. So just to give you a sense, the total number of atoms in the universe is 10 to the 80. So if you have p is 100, then you need sample size is more than the atoms of the universe. So that's not going to happen. So otherwise, you're going to impose a very restrictive model. For example, if you do linear regression, you impose a linear model, and then it becomes a much more restrictive model. It can reduce the sample size you need.
Wenshuo, I certainly appreciate the rigorous notation, but can you give us some intuition as to why do we care about the conditional distribution of y given x?
Yeah, so basically that's the questions listed here. So for example, in the residue question, x would be the residues, and you want to know which axis. So if you know x, basically how stable is your protein, right? That's the distribution of y given x. Think of y as the stability, a measure of stability. Is that okay?
So instead of just thinking of y as a function of x, we recognize that there's some randomness.
Yeah.
So the distribution of y given x is like, the function plus the noise.
Yeah, something like that. Yeah.
Right?
Yeah. For example, you can think of a linear regression, if that makes you understand. Yeah. Okay, since we know it's almost impossible to directly infer fy given x directly, then our first step would be which of the xj's does y depend on? So this is a very important question because even just identifying the important variables already tells us a lot about the distribution, about the question we're studying. For example, if we know for some question that age is an important factor, that already tells us a lot. And if we know that there's a set of xj's y depends on, then we can follow up with some low-dimensional experiments to learn the conditional distribution of y given a really important axis. And now it becomes a much lower dimensional problem. So that's going to be easier. Okay, so that brings us to the question of variable selection. Usually, in practical cases, we suspect the conditional distribution of y given x only depends on a very small subset of x. Although you have a lot of potential variables, only a few of them are going to be influential usually. So our problem is, can we select a set S, which is a subset of 1, 2, 3, P, such that the conditional distribution of y given x only depends on the x's in that set. So if you write down the actual distribution function, then you can see it only depends on the x's in that set. For example, if I have 100 x's, and given those 100 variables, y is distributed as a normal distribution, with mean being x1 plus x3, variance being 1, then if you write down a density, it's going to be like this, where variance is 1 and mean is x1 plus x3, then you can see that this function only depends on x1 and x3 and does not depend on x2 or x4 or other x's. So that means in this case, our s would just be 1 and 3. So although we have, yeah. Yes?
How do you know that it's only the actual variables but not nonlinear combinations of those variables that are the relevant subspace?
I'm sorry, could you speak louder?
How do you know that it's only a small fraction of the x, if the actual xj's and not a smaller subspace that is nonlinear combinations of the xj's?
Oh, so you're saying that the distribution actually depends on all of x's, but only the dimensionality is small? Is that your question?
Yeah.
Well, in that case, then by definition, our S will be the whole set. But we usually don't think that's going to happen in most cases. For example, it's hard to think that. So if you're in GWAS, some genes will be influential. Then I don't know if, like, for example, the sum of all the genes is a factor. It seems less likely, but that's certainly theoretically that could happen.
I guess sometimes in some problems we might not care if there's sparsity in the given basis or sparsity in some other basis, but often we really do care about the given basis because that's the one that's interpretable.
Yeah.
Is that
Yeah, I agree to that. Yeah.
You can always converge to another basis if you want to try that.
Yeah.
Yeah.
But maybe linear combinations of genes or residues are not as interesting to you as genes and residues.
Yeah. That's what it is.
I mean, in image recognition, it would be hard to say this.
Oh, yeah, but yeah.
The features in image recognition are pixels, so you probably don't care
Yeah.
about selecting the.
Yeah, you don't want to select
Whereas
pixels.
our wavelets there actually made a fair bit of sense. So, I mean, yeah.
Yeah, maybe that's just less applicable in that case. Okay, so by this definition, then we're basically testing the null hypothesis. We use H0J to denote it, and that's the hypothesis of Xj are y and y are independent, conditional on x minus j. X minus j means all the other variables except j. So when this happens, then xj is a null variable, which means if you know about all the other variables, then learning this extra xj does not help you predict y. So then xj is not an influential variable here. All right, so then our job is clear now. Suppose somebody collects a lot of data, so with y and x's, and there are n of them in the sample size. Our job is to design a method such that if you give me these data matrix, I'm going to output a set. We call it S hat. So S hat is an estimate of a real set S. And this is basically our answer. Say, OK, just look at the variables in S hat, and that's going to be influential. So of course, the question would be, if I have such a method, how do I know its performance? How accurate is our prediction S hat?
So, sorry, just a question. So is S hat your y hat? Is that your set of y hats, like your class probability, your predicted class probabilities? Or?
Oh, so you remember the definition of S here? S hat is an estimate of S. So for example, ideally in this case, I would have S hat being 1 and 3. In that case, I'm very accurate. But sometimes it's going to be 1, 2, 3. So I make one mistake. Does that make sense?
The set of indices.
Yeah, indices. Yeah, the set of indices. Any more questions to that? Okay, so there are two types of errors, naturally. One is the false discoveries, which means there are some variables that I selected, so they are in S hat, but they're not in S. So if they're not in S, they're not truly influential variables, but I select them anyway. That's a false discovery. And there's a type 2 error, which means there are variables in S that are truly influential, but I have failed to select them. So that's going to be a false non-discovery. And this is also a matter of power, because if you have high power, that means you have a low type 2 error. It means you can select a lot of the real variables. So here's a figure. So this set S is all the true influential variables, and the S hat is the variables I, so we selected, and the intersection are the true discoveries, meaning they are true variables, influential variables, and I have selected them. And here is a type 1 error. All the false discoveries means I selected them, but they're not influential. Here is some real important variables I have failed to select, and everywhere outside is going to be non-influential variables, and I don't select them, so that's true non-discoveries. So obviously, we want to minimize type 1 error and type 2 error, but of course, it's very hard to do both at the same time, so we have to have some priority. And our priority usually is going to be the type 1 error, so we want to control type 1 error first. We'll see why that's the case in a minute. So, okay, so how do I actually reverse define the type 1 error and type 1 error rate and control them? So this brings us to the definition of FDR, the false discovery rate. Before that, let's define the false discovery proportion, which is called FDP. That's basically the number of false discoveries divided by the number of total discoveries. So like what proportion of my discoveries are false. For example, if I have selected 5 variables, x1, x3, x4, x9, x12, and if 3, 4, and 12 are real discoveries and 1 and 9 are false, then my false discovery proportion is going to be 2 divided by 5, because I have 5 discoveries, 2 of them are false. That's 2 divided by 5.
Wenshuo, do you mind doing the Venn diagram of this example on the board? Like with a marker, just the concrete example with the concrete indices that you have.
Okay. Where's the board?
You can do the example in the next class.
Yeah, sure. This is the board. Oh. Okay, so for example, if I have, can everyone see this? This is our set S, the truly influential variables. This is what I discovered. And the intersection is going to be the real ones, 3, 4, and 12. And here is going to be the false ones, 1 and 9. And here is whatever. Say if 2 is here and 5 is here. Does that make sense? So this is a set of, ideally, I want to find this set, but here's what I have, and I want to know how many of them are false. So basically, how many variables outside S that I have selected anyway. Does that make sense now? Yeah, and of course, that's going to be a random number. So we define its expectation to be the false discovery rate. So that's just the expectation of the FDP. And of course, we want to lower FDR because, for example, if I tell you here's 100 variables that might be important, and it's going to be very different if I tell you that only 10% of them are actually false, which means if you study this with these 100 variables, 90% of your money is going to be well spent. But if I tell you that here are 100 variables, but 40% of them can be false, well, that's going to be like around half of them are really important. So we really want to have a very low FDR so that we're really confident about our discoveries.
So what are you taking the expectation over here? What's rand?
That's a very good question. So there are several things you can do. So usually we take that expectation with respect to both x and y. So we are treating x and y as random, both.
And then normally your procedure would be deterministic given the data.
Yeah, that's right.
Okay.
So our goal here is to first control the FDR, which means we do not want our FDR to be high. And under that restriction, I want to make as many discoveries as possible. Any questions so far? Okay, so before we go deeper, first we're gonna take a minute and discuss what we do if we have highly correlated covariates. So just imagine if there are two variables, say x1, x2, they are so highly correlated, then the definition of S, which is the truly influential variables, the definition can be problematic in practice. So think of the case if you do a linear regression and your design matrix has two very highly correlated columns. So in that case, it's going to be almost impossible to distinguish which one of the x1, x2 is really important because you only have a finite sample size. So in that case, we might need to group covariates and redefine the FDR. For example, if x1, x2 are really correlated, say 0.99 correlation, we're not going to find the difference between them anyway, so we're going to just group them and call it G1. And similarly, if 3 and 4 are correlated, I'll group them, call them G2 and G3 here. So now our false discovery will be defined on the group level. So for example, here, the same example, just with X replaced by G. So we're going to select groups, and we're going to say, for example, if 3, 4, 12 are the true groups, 1 and 9 are the false groups, then my false discovery proportion is again 40%. Does that make sense? So if you have highly correlated covariates, you're going to group the variables first. Okay, so now that we have a well-defined problem, let's talk about solutions. So everybody knows what a p-value is. Science builds upon p-values. When we have a null hypothesis, then we also want a p-value, which is a matter of evidence in the data that's against our hypothesis. So there are a lot of works on finding p-values in many settings. Let's remind ourselves, our null hypothesis is xj conditionally independent of y given the other axis. So in linear models, if you are doing a linear regression, this is equivalent to testing the coefficient for xj is 0 or not. And if we do have valid p-values for the null hypothesis, we can plug them into the Benjamin-Hochberg procedure. And this is a procedure which is, well, you adaptively choose the rejection level, so you make a decision on each hypothesis sequentially, and then you can get FDR control. There are some assumptions on the dependence of the p-values, but that's a matter point as far as we're concerned. So for example, if we are in a low-dimensional linear regression, then we can always find p-values, which is if you subtract the real beta j from beta j hat divided by the standard deviation, you're going to have a t distribution, and you can design a rejection region based on that. So and then you can get a p-value from that distribution too. However, if you're in high-dimensional settings or nonlinear models, then it's going to be very hard to get both valid and powerful p-values. We just don't know how to do them in a lot of the cases. Okay, so now what do we do? So a very natural thing to consider is how about we just test the marginal dependence? So I call it H0j prime, which is how about I just test if xj and y are independent marginally without conditioning on the other variables. This is definitely something people do. It's really good for exploratory analysis. Basically, I want to have a rough sense which of the xj's could be important for y. And also, this is a right hypothesis if you care about the reverse causality, which is what variables does y affect. For example, in some microbiome studies, you might want to know that if I have a certain disease, the disease would be y, and how does that affect my microbiome composition? So some cases that's what you care about, and in that case, this will be the right hypothesis. If you see a dependence, that means y affects x. However, in our setting, this is not valid. This is the wrong hypothesis because we want to find which axis causes y. So that's the reverse of the causality of what I just mentioned. So in that case, the true hypothesis is going to be conditional dependence and not marginal independence. So we're going to see that through example. Are there any questions before?
Sorry, in your explanation of reverse causality, right, which xj's affect y? And then for the normal causality, it's which xj's cause y?
No, which xj's does y affect? So which
Y affect.
so y affect which x's?
Can you explain more why the marginal testing is the other direction? I didn't quite understand.
So for example, if you have like if x1 causes y, okay, if we know that x1 causes y, then if x2 is correlated with x1, although x2 does not directly cause y, but if you see x2 and y, just the two of them, you're going to see a correlation, right? So that's why if you see a correlation, that does not mean that xj is actually influencing y.
I think the question was why, the second bullet point.
Yeah.
Oh, okay.
Why is this a right hypothesis? Why is marginal testing the right thing to do when we think y causes x?
Yes.
Okay, so if y causes x, then definitely they're going to be dependent, right? That's the definition of y affects x. Does that make sense? If I say like the disease affects some microbiome composition, like a certain species, that means they're not independent, right? If I have the disease versus I don't have the disease, it's going to be different. So
What about concluding non-causative? So I think that what you want to, if x2 doesn't cause y,
if x2 doesn't cause y,
then are you saying they're marginally independent?
not really,
No,
because it could be correlated with a truly influential variable.
right?
It's a matter of controlling for confounders.
Yeah.
Okay.
So if we think that y causes x, there are no other confounders because there's only one y.
Yeah.
And so then it is really the conditional hypothesis because we don't have any other variables to condition on, we don't have any possible confounders. But when we think the x's cause y, we have to control for all the other confounders, which are all the other x's.
Okay.
And that's why we need a conditional hypothesis.
Yeah, we can see this more clearly through this example. Yeah, so as I said, they're not equivalent hypotheses. So think of a linear regression, then the real hypothesis H0J means beta J is 0, but that does not mean that they are uncorrelated, right? The hypothesis H0J prime is saying that they are uncorrelated, but that's not equivalent to beta J is 0. So here's a very simple example. If I have these 50 observations and 200 covariates, and now I introduce correlation between the adjacent axes. So x1, x2 are correlated, x2 and x3 are correlated, and my y depends on the x2, x4, x6, and x8, x10. So basically the even indices up until x20. And then if I just test the marginal hypothesis, I'm gonna see a very large dependence between y and say x1, because x1 is highly correlated with x2, and x2 is a truly influential factor. So although x1 does not directly affect y, but since it's correlated with x2, then we're gonna see a very high dependence between y and x1. And that makes me select x1, and that's gonna be a false discovery. So if you just use the marginal p-values, then what we're going to see is the FDR is around 64%. So basically, 64% of discoveries are wrong. Yeah?
SS, why are you saying cause as opposed to just correlation between influence between x and y?
Because you want the scientific question is really about causality, right?
You really infer the direction of effect.
The direction of effects is something you assume. Like for example, you believe that the gene mutations cause you some disease, not because you have some disease and then your gene mutates.
I would believe that my mutations are correlated with disease, but saying that something causes something else is a much stronger assertion.
Yeah, I certainly agree to that. But I think, at least for example, for gene mutation cause disease, I think that's something we can safely assume. For like, we know that's related to gene mutations.
Unless it's cancer, but
Not cancer, right?
This is kind of silly, right? Like we know there are situations in which things cause other things.
Yeah.
And assume that happens sometimes.
yeah.
Yeah.
doesn't happen all the time.
If you want to.
It's not that, I'm not saying that you can infer that from the data, just
Yeah.
that it is an underlying truth.
Yeah.
There you go.
Yeah.
This is Wenshuo's answer, so
Right,
Yeah.
I agree.
Yeah. Yeah, there are definitely some times where you're not sure if the causality exists, and that should be something you do before you do this.
I mean, you have to take into account every other possible explanation.
Yeah.
It's a non-statistical hypothesis.
Yeah.
But if you can, it's a non-statistical assumption. But if you can make the assumption that X causes Y and Y doesn't cause X, then that's the non-statistical part. The statistical part then is testing this null hypothesis. You test a different null hypothesis, you're getting the wrong answer, even under the assumptions that only X can cause Y.
I would think the null hypothesis was that say in the case of genotype, the genotype was uncorrelated, that it was like it was normally distributed, and you were testing for some difference in the distribution in the presence of, right? It wouldn't,
Depends on the causal question you're asking. The causal question you're asking is like, does this mutation cause this disease? Then you need to control for the confounders, which are like all your other mutations, for instance. And so it's not a partial
influence. I would say it influences disease unless your genotype never causes anything. It's always presence in there.
No, well,
So
I'm not a biologist, but
the context of Mendelian randomization, that there are situations where you can then claim causality as a result. And it's we can talk after. Yeah,
Okay.
it's pretty standard in genetics.
Okay. So what about the simple cases where the covariates are independent? So there are no dependence among axes. Then conditional dependence will imply marginal dependence, but not vice versa. So this is a very simple talk example. If I have two ID Bernoulli half random variables, so that means they are independent and they are 1 and they are always probabilities both a half. And Y's response is 1 is if x1, x2 sum up to 1, and if not, then y is 0. So as you can see, x1, x2 together completely determines y. So if you write down the distribution of y given x, that's going to depend on the whole set. So x1, x2 are both true variables. However, if you test them marginally, you're going to see x1, x2 are both independent of y marginally. So if you know x1 is 1, it doesn't tell you anything about y being 1 or 0, because that's still going to happen with probability of half each. So if x1 is 1, then y is 1 if x2 is 1, y is 0 if x2 is 0, both happen with probability of half. And if y is 0, still y is going to be 1 and 0 with a half probabilities. So you knowing x1 does not help you predict y, so x1 and y are independent marginally. So if you do marginal testing on x1, x2 with y independently, then you're not going to discover anything, which is very bad because in this case, everybody is influential. So as you can see, you're going to lose. So of course, this is a simple talk example. You don't expect this to happen in real settings, but what could happen is you lose power by only looking at the things marginally. Although in the cases where the covariates are independent, that's kind of a right hypothesis, but you lose power, which means you're going to have a very high type 2 error, so you miss a lot of the important variables. Okay, and also an issue with marginal p-values is something we have been talking about a lot, which is the correlations among the axes. For example, if I want to study what could be causing cancer, so our response y would be whether a person has cancer or not. And if we do marginal testing, we're going to discover both age and retirement is going to be significant because the marginal p-values are 0.01, 0.02, below 0.05, our magical number. So we're going to conclude age and retirement are both influential. However, if we look closely, we might think that age is actually a really important factor for cancer. Retirement, however, does not directly give you cancer, and it's significant marginally because it's highly correlated with age. And another example would be if you are studying for a trait what SNPs are causal, then you might discover both SNP1 and SNP2 are marginally significant, but you wouldn't know which one of them are the true influential SNP. And of course, if you only have 2 of them, then you might get the right answer by looking closely. But if you have like 1,000 of them, then you don't know what to do. Okay, yeah, I'm just out of time. Yeah. So this is this is a Manhattan plot of GWAS, so each of this represents a SNP. And you can see if you just test the marginal p-values, you're going to see these bumps there. And what people really do is set up a cutoff and claim here's discovery, here's discovery. But of course, this is some post hoc fix. We don't know how to rigorously define a bump and if I do that, do I get FDR control? We don't know that. So we lose the statistical guarantees. And of course, we can also try to be Bayesian. If we cannot do marginal p-value, then maybe we can be Bayesian. For example, this is a very simple setting where we're doing a linear regression. And we put priors on all of our parameters. And this is a very good way to incorporate domain knowledge. So if you have some prior knowledge about which variables might be important or how many variables are going to be important, then you can incorporate this into the prior. And this is a very good way to do that. And once you have posterior probabilities, so you're going to have posterior probabilities of a variable being non-null. And if you have that, then you can just set a threshold and control the Bayesian FDR. Now everything is very simple because you have, by being a Bayesian, you have a direct probability statement on the thing on the parameters. So it makes things much easier. So this is a simple setting. So let me explain this a little carefully. So sigma square is going to be the noise, and this tau you can see this as the signal to noise ratio. And this gamma here is an indicator of whether the term xj is influential, because if gamma j is 1, then beta j is non-zero. And if gamma j is 0, then beta j is 0. And when beta j is 0, that means xj is a null variable. And we assume gamma j is Bernoulli alpha. So alpha is basically how many variables are actually important.
So do the statistical geneticists in the audience recognize this model? Does this slab model we use to simulate?
Yeah, this is
phenotypes.
Yeah, this is like the simplest model I can think of. And okay, so by being a Bayesian, there's a price you pay, which is you're gonna pay a big price in computation. It could be a huge issue. So usually it's gonna be hard to have a prior that's both accurate in that it really reflects your knowledge and is computationally efficient. It's always hard to achieve both. And also a more important issue is in a lot of cases we have a very small sample size and the results is going to be very influenced by the choice of prior. It's going to be sensitive. So here's a simple simulation. My n is 50, p is 100 as euro, and my alpha 0 is 0.1. Alpha 0 is what proportion of the variables are important. So 0.1 means roughly 20 variables are important. So that's 1 out of 10 into 100. And tau 0 is 2, that's a signal to noise ratio. And all the other variables are, you don't have to, it's just the parameters for the noise. So let's control the FDR at level 0.1. So we want to make the claim that 90% of my discoveries are true. Then I'm going to use priors with every other parameters being well specified. So I'm going to use alpha is 0.1, and v and s squared are 1. They are all well specified. I'm only changing the value of tau. So vary tau from 2 to 3, 4, 5. And you can see if tau is 2 means everything is well specified, then yeah, we can control the FDR at level 0.1. But if my tau is misspecified, then we're going to see the FDR really going to grow quickly, and at the end it's almost 0.5. And this is also very, very well specified setting because all the other variables are true. I'm using all the true variables for parameters for all the other parameters. And this is, you never have this in the real life setting because you don't know, you can't possibly know all the other parameters. And also the linear model could be wrong. So you can see it's very dependent on the model being correct. So it's very sensitive to your prior. Okay, so now that we know marginal p-values and Bayesian FDR, they don't do quite what we want. So what about machine learning? So we have a lot of machine learning methods that could help us, like lasso, neural networks, random forests, and they produce sparse models, and they are very good at prediction. So it's chances are they are learning some very important aspects of the condition distribution. And the problem is then just, can we translate those results into rigorous statistical inference? So how about we just start from lasso, the most simple example we can think of. Lasso is a lot of researchers' default choice to do variable selection. And here's the very simple definition. So basically, you want your x beta to be close to y. So here is the L2 norm of a difference. But you don't want a lot of non-zero betas. So you add an L1 penalty here, and lambda is a parameter you choose. And this L1 penalty will make your beta sparse. And we can consider an xj selected if the coefficient for xj is not 0. The lasso coefficient for xj is not 0. So, of course, there's a very important tuning parameter lambda, and that plays a very important role, as you can see here. So if you increase lambda, then all the coefficients are going to be roughly decreasing, and eventually they're all going to be 0. So it's a very important question, what lambda do I choose? So if I choose lambda here, I'm going to only have 2 important variables. But here, maybe I'm going to have 15, something like that. So lambda is very important. You've got to specify lambda. And how do I choose lambda? Well, people do cross-validation. So basically, we separate my data sets, and I estimate my beta on one set and evaluate the performance of that estimate on the other set. So for example, if I do twofold cross-validation, that means I separate my data set into D1 and D2, 2 sets, and I'm gonna fit my beta, say, on D2, and then I'm gonna test it on D1. So this would be the mean squared error on D1 with the beta estimate from D2. And symmetrically, we estimate beta on set D1 and then test it on D2. So of course, if I sum these, then I define this as a function of lambda. I want to minimize this function because if a lambda that makes this small, then I can say that, well, that's a good lambda we can use.
Good for what, though? Here, I guess it's good for prediction.
Yeah, it's good for prediction. That's the point.
But that's right. But that's sort of different from what you were talking about before.
Yeah. That's a very important point. That's a very important point because the idea was, like, if they're good at prediction, then they're capturing some important variables, perhaps. So we want to know if that's the case. And of course, as Alex said, as cross-validation minimizes the prediction error, so it doesn't really penalize the inclusion of the null variables. So I don't mind if I have a null variable in my model, as long as I don't miss the important ones. So here's a really, really simple setup. So I have, again, 200 variables, and my y depends on the first 10 variables, and my noise is really small. The variance is only 0.01. And if I run lasso with cross-validation, then I did 100 experiments, and in all of them, I discovered all the 10 important variables. There's no problem there. I discovered all the real variables. However, the FDR is definitely not controlled. As you can see, it's concentrated around 0.6. So I discover all the important ones at the price of including a lot of null variables. So this is not good for our purposes. Okay, so then how about we try to extract some information from the lasso and turn that into p-values? Can we do that? To do that, we need a measurement of variable importance, and one natural choice would be the largest lambda at which a variable is selected. So if you look at the lasso path, then, for example, this variable gets selected before this variable because it's earlier on the path. So we can say this variable is more important than that. And we can just use this value to evaluate how important that variable is. However, we cannot derive the null distribution of these statistics because it's unknown and it depends on the actual distribution of I given x. So that means usually we cannot just directly translate them into p-values. However, we can translate them into p-values asymptotically, but we need very strong assumptions. And in practice, we cannot have because, for example, one assumption would be I have a linear model and the number of non-nulls, which means the number of true influential parameters, is of the order square root of n over log p. But, for example, if n is 1,000 and p is 10,000, then I'm going to have roughly 9 non-null variables, which is, of course, not something you can assume in practice. So these are not promising practically. And also, there's this more severe issue is there are a lot of asymptotically good properties of the lasso, but people tend to overinterpret them. It works well in a lot of settings, but it definitely does not control the FDR. And there's a very extreme case, which is even if you have independent covariates and there's no noise, there are still cases where you cannot make both type 1 type 2 error with small with any lambda. So that means with any lambda, you either have a very high type 1 error, which means you select a lot of null variables, or you're going to have a very large type 2 error, which means you select a lot of non-null variables. So you really cannot have FDR control using lasso. Okay, summary. So marginal p-values, the first approach we have, they are very easy to compute, a lot of methods to do that, and they're useful in a lot of cases. However, they're not valid for FDR control, and most of the time they need post hoc fixes, like the Manhattan plus. You have to define a bump and a cutoff. And also, the method either has very low power, or we don't have any statistical guarantees over those methods. And by being a Bayesian, it's very good if you know how to incorporate your domain knowledge into a prior. If you can do that, it really helps you a lot. However, computationally, it could be challenging, and also it's very sensitive to your choice of prior. And finally, if you do joint analysis with the machine learning method, then it's going to be really powerful. And however, we cannot get practical p-values from those methods. Any questions so far? Okay, so this is the last slide. What are we missing, right? So this is certainly not a hopeless problem. So what are we missing? Well, we've been talking about f y given x, which is a conditional distribution of y given x all the time. But actually, we could have a distribution of the covariance x too. So, however, most of the conventional methods, they assume like a rather strong model on fy given x, but they assume very little about fx, and a lot of them even conditioned on x. For example, if you do a linear regression, you're conditioning on x, which means you're treating x as constant. You're not considering them being random at all. So what if there is something to exploit in the distribution of x? And it could be argued that in a lot of cases, we know a lot about x because we can study x, but it's going to be expensive to collect the response y. So usually we know a lot less about fy given x than fx. However, in conventional inference, we completely ignore the distribution of x, the information hidden in the distribution of x, and that's where Lucas will come in and tell you how to extract that information and use that to help us do inference and variable selection. Thank you.
I am a statistician in the Harvard Department of Statistics. Wenshuo is one of my students. We're doing some really great work related to this. Cool. So what I work on is variable selection, in particular in high dimension or nonlinear models. Of course, it works in linear and low dimensional models too, but the challenging problems are those. So I'm going to tell you about this, and I would love to hear from you guys at the end. I'll have a plug that I want to hear about your problems that you think this might be related to. You know, I'm going to talk about what I know, which is the method. I'm going to try and show you as many pictures and give you the intuition for what I'm doing and why it works. I'm going to talk a little bit about the application to GWAS at the end, but since I'm not a biologist, I don't want to spend too much time on that for fear of saying something wrong. So I hope that you guys can all imagine in the audience applying this method to your work and ask me questions and see why it should work for you. So let's get started. So the problem statement, so this little subsection will sort of be a summary of what Wenshuo just went over in his excellent primer. So this is the Cliff Notes version. So we're doing controlled variable selection. We have some outcome of interest, y. I'm going to call it a response or dependent variable, whatever you want to call it. And we have a whole bunch of possible explanatory variables or features or independent variables or covariates. And the question we're asking is how can we select a subset of those variables that are important and not make too many mistakes? That's the high-level question. Hopefully I don't have to convince you that this has lots of applications in biology, genomics, healthcare. Hopefully there are some that you know about that I have never even heard about, and I would love to hear about them. but this certainly comes up in economics and political science, in industry and technology, where your responses are, diseases or future income or political outlook or whether a user clicks, and your covariates might be genomic variables like SNPs or gene expressions. They could be electronic medical records. It could be socioeconomic demographic variables. Here it could be browsing history. All of these things, you have questions where you have lots and lots of potential explanatory variables. You want to use them to explain some outcome of interest y, and you want to select a small number of them that are going to help you both interpret but also give you scientific insight into the process that drives from x to y. All right, so again, review from Wenshuo's talk, but what is an important variable? This is my definition of an unimportant variable. So if a variable is conditionally independent of y, given all the other variables, x minus j being everything but the jth variable, then it is unimportant. And I think this is a natural definition. Indeed, if we put these together, it's called the Markov blanket. This was the S that Wenshuo was talking about, so I'm also going to use S. This is a well-defined object. Note that there's no model here. Let's just assume that y and x have some joint distribution. And this Markov blanket is well-defined. It's the smallest set S, such that if I give you all the x's and tell you what S is, you know that you can throw away all the variables not in the Markov blanket without losing any information about y. And you know that if you throw away any variable in the Markov blanket, you have immediately lost the ability to predict y to some extent. Question, Artie, please.
Yeah, so are you eventually, I don't want to like derail anything.
No, go nuts.
But if you're, I'm just wondering for, like in our situations, in gene expressions, often there's interactions between variables, so it might not, if you independently change the gene, that might not influence the outcome, but if a couple of them change together, then you get a very strong effect.
Yep.
That's completely out of this.
Nope, that's totally in this situation. So if a covariate affects y through an interaction, then it is very much important because you're conditioning on all the others, right? So because in an interaction, right?
If you fix the other ones and you change that one, then nothing would change.
Well, then it's not an interaction, I think, right? An interaction means that if they all vary together in the right way, right, that there is some setup of the other variables that this one, right? If when you fix all the other variables, for every setup of the other variables, and change xj, it doesn't affect y, then it is not interacting with the other variables and causing y.
Yeah.
Right? If I think of y equals x1, x2 plus epsilon, then when I hold x2 fixed,
So these are
changing
independent?
x.
So these are all assumed to be, I'm sorry.
No, definitely not. I'm assuming nothing about the joint effect.
Just very practically speaking,
Sure.
what will happen for us is we have a ton of correlated variables. So let's say we have
It's going to be my next slide, by the way.
blocks of correlated variables, right? And so if you go back, if we just did this naively,
Yeah.
and we would end up with 0 important variables.
Yeah.
And because basically you'd see teeny little fluctuations in xj.
Well, you'd end up with zero. You'd end up finding 0 important variables. You have important variables, right?
Yeah.
This is not data connected. This is the ground truth, right? This is a definition. This is what I'm going to try and find. And you're right that we won't be able to find them, which is exactly the top of my next slide.
Okay.
Yeah. So I'm going to address that. But I think that's not dealing with interactions, right? The thing with interactions is if like.
Yes, right, okay, thank you.
We're with me? Okay. Great. All right, so I was here, right? So we have the Markov blanket. So this definitely allows for interactions, and that's really important because that's one of the things that, if we fit a linear model, we're not going to find interactions if we don't add we have to manually add interactions, whereas this automatically is looking for all interactions. All right. Again, as Wenshuo mentioned, if you fit any kind of generalized linear model, including the usual linear model or logistic regression, this null hypothesis is exactly equivalent to testing the usual null hypothesis we test, which is whether the coefficient on the jth variable is equal to 0. So it's what you're used to when we do have a model, but I'm not going to assume a model for y given x. And then we want to control the false discovery rate, which, again, is the variables that you select in S hat. S hat is the set we select that are actually unimportant. So these are the false discoveries divided by the number that you select in total. And we're going to take its expectation. We want it to be something small, right? So that we can interpret our set. We want to be able to say something like, here's a set of variables S hat, and I expect 90% of them to be important. So you could go off and investigate these variables in a low-dimensional setting, as Wenshuo mentioned, or they may tell you something by themselves as a group. All right, so let me address this excellent point, which comes up often, which is why I have it in quotes. because I hear people say this to me a lot. So if we have variables that are highly correlated, then what goes wrong, right? We basically have insufficient information in our data to confidently reject any of those variables, which is definitely what I need for FDR control, right? If I want to control the FDR below, say, 10%, then I sort of roughly, intuitively need to be about 90% certain that any given variable is important. And if two variables are basically identical, I'm never going to do better than 50%, right? And so, okay, so that's a problem. And basically what it says is we're asking the wrong question, right? For our data, we don't have the resolution to do this. We're asking the wrong question. And so what we're going to do is we're going to change the resolution. So we're going to group variables. So this is the, I learned this symbol when I was writing this talk, actually. I didn't realize that plus meant disjoint union, but this is a disjoint union of GK. So I'm just separating my variables into groups, disjoint set of groups. So I'm putting my correlated variables together and saying, look, I'm not going to be able to tell you which among this group is important, but I can tell you that this group is important, maybe. And so I'm going to do that, and then I can do everything that was on the previous slide, everything Wenshuo talked about, in terms of those groups. So I can ask, which groups are important, defined this way, where x minus gk is everything except for the variables in gk. I can define false discovery rate analogously. So now I'm selecting groups. So this is a set of groups. And I'm going to say what of the k in my selected groups, which of them contain no important variables. Right? So a false discovery is if I select a group and none of the variables in it are important. And then I'm still going to divide by, that should be a k. It doesn't really matter, but the number of elements in SG. And we still want to control that below Q. And the point I want to make, I'm not really going to talk about this more, but everything in this talk seamlessly transfers to this setting. It's like really easy. It's actually one of the nice points about this work is that moving from single variables to multiple variables, to groups of variables is like totally trivial. And there's a paper basically that shows that like, once you know how to do knockoffs, doing group knockoffs is like totally straightforward.
But you have to know how to group.
Yeah.
You do have to know how to group, and that is absolutely a challenge. It's something that Matthew Stevens talked about in his talk. It's a really interesting question. That's not something we're going to address.
In the setting of genetics with SNPs that are in linkage disequilibrium, it's hard because it's kind of these groups kind of slide along, and it's not clear, where.
It's not clear. I think there are reasonable heuristics you can do because you can look at the x's, right? So you can see the ones that are highly, highly correlated, right? It's not like these groups are totally mysterious, but where do you set the cutoff for correlation? Definitely a question. I don't know how to answer that, and it's an important one. But there's at least something we can do if we know something about the grouping of our variables. Yeah. All right, so here's a sneak peek of what I'm going to tell you in this talk. So I'm going to talk about model X knockoffs is the full name for this method because there was another iteration of knockoffs before this. But model X knockoffs is really I think it's the real deal. The author of the original knockoffs paper also thinks this is the real deal, so it's not just my personal bias as an author of this paper. So what it's going to do is it's going to use knowledge of X's distribution. This is what Wenshuo referred to in his last slide, that we're actually going to not model y given x, we're going to model x. And we're going to use that information to solve the controlled variable selection problem. And again, we're going to assume no model for y given x. And we're going to allow any model for the x's, unlike being forced to use, say, a GLM for y given x. We're going to allow any model for x. We're going to be in any dimension, so there's really no difference between low and high dimension in the way we do these things. It's totally different from, say, linear regression, where you have to completely change what you're doing when you move from low to high dimensions because the maximum likelihood estimator becomes ill-defined. We're going to get exact false discovery rate control. There are no asymptotics in this talk. Everything is exact. And we're going to have practical performance on real problems, which of course is what matters to me, matters to you all, I hope. And that's really talking about power and the fact that, and the fact that we're robust to the assumptions we make about X. All right, so I can talk about that a little bit. So we applied this to a GWAS data set that had about 5,000 subjects, about 40% had Crohn's disease, about 400,000 SNPs for each subject. And in the original analysis of the data, they used marginal p-value testing, which Wenshuo went over. And we know that's not quite testing the right hypothesis, but there are post hoc fixes you can do. And you can make certain arguments to try and control the false discovery rate at 10%. And they did. They made 9 discoveries. We run our method. I think we have a much more credible argument that we're actually controlling the false discovery rate at 10%. And we have double the power. So I'll talk about that at the very end. All right, so this is a one-slide overview of most of Wenshuo's talk, which is that other methods that are out there, marginal p-values, excellent exploratory tool. They're not really answering the right question when we think of x as causing y, and as a result, we can either lose power, or FDR control, or interpretation, or all of them when the xj are correlated. Bayesian inference is a great way of incorporating prior information, but we have computational challenges and we have sensitivity to the prior that can make this hard to both implement in practice and maybe believe our results. And lastly, there are lots of tools from machine learning. They're excellent for prediction. However, cross-validation would be the normal tool we use for model selection or variable selection, and it's really not going to do what we want here, which is have a small type 1 error rate. It's going to give us lots of false discoveries. And doing precise statistical analyses, there has been a lot of work trying to do this for like the simplest of machine learning methods, things like the lasso. But still, those methods make some very, very strong assumptions, which at least I find quite unrealistic in practice, especially as compared to the assumptions I'm going to make in this talk. But that said, I'm actually going to use a lot of the methods in especially Bayesian inference and machine learning, the things that can be very powerful but don't necessarily come with as reliable inferential guarantees. That's what sort of I'm going to build knockoffs over, because knockoffs kind of acts as a wrapper around any method that you want. And so let's talk about that. So knockoffs is the method. And here's the view from 10,000 feet. So you have a data set. So I talked about these random variables y and x. Now I'm going to talk about concrete vectors of actual data samples. So I have IID samples, and my y's are stacked into this vector y. My x's are stacked into this vector x, so I have n samples. And again, there's p columns because I have p components in each x, so p covariates. So you have data, and I'm going to assume that you have some way of measuring variable importance. And I'm going to let that be completely arbitrary. So you get to decide using whatever scientific information you have in your head, whatever you ate for breakfast that day, however you want to choose that you want to measure variable importance, you can use that method. So zj, I just need, if you have your x and y, you have some algorithm that takes in x and y and spits out a vector of zj. So 1z for every variable, that's some measure of variable importance. And so, for instance, something that would sort of always apply is you could fit a machine learning method and see how much the cross-validation error changes when you drop that variable, right? That's some measure of how important that variable is. If it changes your prediction error, it seems like it's probably important. If your prediction error doesn't really change when you drop that variable, it doesn't seem like it's very important, right? I'm not going to say that that has any inferential guarantees, but it seems like a reasonable measure of variable importance. There's lots of things. You could fit a linear model and take the coefficient estimate. Usually it's absolute value. You could fit a Bayesian method, take the posterior probability that your variable is important. Any of these things are good. If you think it's a good measure of variable importance, I'm happy for you, and I'm going to let you use that. Okay? So that's what you have. And lastly, you actually want to do some sort of variable selection, and you don't want to make too many mistakes. And so you have some desired false discovery level Q, but you really don't have statistical properties for these ZJs, and so you don't really know how to control it. In particular, you don't know the null distribution of ZJ, right? If XJ were unimportant, if we knew what the distribution of ZJ were, we could turn ZJ into a p-value and use this. But the problem is we don't know this, especially in high dimensions and nonlinear models. We really have no idea how to do this properly. All right, what knockoffs is going to allow you to do is use your variable importance measure. Again, you get to pick that however you want. And I'm going to give you a subset of variables that controls the false discovery rate. So here's the picture of what I'm talking about. You have data. You are going to choose some variable importance measures, one for each variable. I am going to take that, put it in a box. It's almost the holidays. I'm going to wrap it up nice with a bow on it. And then I'm going to feed that into knockoffs. So knockoffs really, it just takes that box and it spits out an S hat, which is your set of your predicted set or your estimated set of important variables. And it's going to control the false discovery rate at the nominal level Q exactly, non-asymptotically in finite samples. And for the rest of the talk, I'm going to talk about the method itself, why it works, how it works, and what assumptions I need to make.
So wait, what is the discovery rate? Like, how are you measuring incorrect discovery? Is it according to your personal measure of importance? It's just according to the original measure of
according to the truth, yeah, underlying truth, right? So I of course don't get to observe the false discovery proportion, right?
No, I know, but I'm just saying you're measuring it according to whether it's independent. This is like the
Conditional independence, right? It's the H0J, yeah, right? Which is the right question to ask, for instance, if you want causality from X to Y and you're controlling for all the other X's, right? Yeah, another question.
So I thought P was the total number of variables.
P, yep.
You don't have to go to so like,
Sorry, can you say again? P is the total number of variables, yeah?
right, but then you subset it as like at the end, it's still P, right?
S hat is a subset of 1 through P, yeah? Yeah, so I'm just saying it's any subset, right? I'm going to spit out some subset. I'm just saying what S hat is, yeah. Sorry, yeah, question.
You're basing your class there, or are you just putting in these important labels for the X's that you're given, or do you just maybe calculate that for?
Yes, so good question. Yes, there is, of course, some approximation in this picture, and the approximation is that this box is the algorithm that takes in Y and X and spits out the ZJs. So I'm going to need your computational algorithm that spits that out, and I'm going to apply that in a slightly different way, which I'll describe soon. Yeah. But I am still using your ZJ. Really, I'm not using the ZJs themselves. I'm using the ZJ, the function that generates the ZJs.
So the ZJs don't need to be real numbers with some monotonicity, and like there's no.
They need to be real numbers.
Okay, but like you said, no statistical property.
If you give me imaginary numbers, I'm gonna.
Does a bigger ZJ have to mean more important? Like you do need.
It doesn't have to, but it's not going to be very powerful if it doesn't. So you know, if smaller ZJ means more important, you should probably flip it.
Okay.
I'm just so confused. Okay, maybe I'll just let you talk.
I mean, this is the 10,000 feet. I'm going to lower the number of feet over the course of the talk, so hopefully that'll help. But it definitely, if I get to the part, I finish the slide, and it doesn't make sense, definitely stop me. Okay, great. All right, so this is in a lot more detail what I'm going to do. But still not really describing any of the steps, but at least writing down the steps. Okay, so in the first step, I'm going to construct knockoffs. So the name of the method comes from these fake variables that I create. And so basically, I'm creating proxy variables for each of my original variables. So I have P columns in my original data set. I'm going to create P new columns on a computer. I'm not going out and collecting new data. Creating P new columns of fake data that somehow need to mimic the original data in some way, but are all going to be, they're fake, right? So they're all null variables by my definition. And I'm going to use those as sort of controls for my original variables. That's sort of the intuition behind what purpose they're going to serve. Then I'm going to compute knockoff statistics, and this is where the variable importance measure comes from. Because what I'm going to do is, as alluded to, I'm not just computing variable importance measures for my original variables. I'm going to compute variable importances for all the variables and their knockoffs. So now I have 2p of those z's. So I call them z1 through zp and z tilde 1 through z tilde p. I have 2p of these variable importances, and I'm going to basically look at the relative importance of the original and knockoff variables. And the idea is that since my knockoffs, I know they're fake variables, that's going to give me sort of some sense of the null distribution of my original variables' variable importance measures. So if my knockoff variable importance and my original variable importance for the jth variable look similar, that seems a little fishy, right? That suggests that that variable probably isn't very important because I just made a fake variable that looked about as important as it. But if my original variable has a very big variable importance relative to its knockoff, maybe that says that this is an important variable. That's the intuition behind what the WJ captures, is that difference between the two. And again, I'm going to make all these precise soon, but that's really the intuition. Then we plug it into this slightly, more than slightly, weird procedure, but you know, it's not too crazy. I'm going to order these by decreasing magnitude of WJ. Right? We expect big positive differences to correspond to the good variables, right? So I'm going to start with big, although it could be positive or negative. Then I'm going to go down the list and only keep the positive ones. And I'm going to keep track of some sort of estimate of FDR hat as I go down this list. And as soon as that FDR hat gets too high, I'm going to stop. Again, I'm going to make this precise, but that doesn't seem like too unreasonable thing to do. It means I'm only selecting the largest positive WJs, if that makes sense. And I'm stopping when some estimate of FDR hat goes above the level I think it should. Okay, so the key to what makes knockoffs work, and I'm going to come back to this a few times in the talk, is that steps 1 and 2 are constructed to have this super important coin flipping property. And it's really this symmetry that makes knockoffs work, and I think also gives the intuition for why it should work, even approximately if things aren't quite perfect. And so what we want is that the null WJs, right? We could think of this almost like a p-value. It's not a p-value, but what do we know about a p-value? A p-value is defined as under the null, it has a certain distribution, which we know, right? That's what makes a p-value useful, is we know its distribution under the null, and then it usually has some other distribution under the alternative, but we don't know what it is. That's OK. So it has some distribution that we know under the null, and that's the purpose that these WJs are going to serve. Is that so for the null WJs, we know that their signs are coin flips. And in fact, they're independent coin flips. And they're independent coin flips even after I condition on the absolute values, which is how I'm going to order the variables. And so it's sort of this really, really strong null distribution property that I'm getting out. Note that p-values, usually when we compute a lot of them, we do not know anything about their dependence structure, even among the nulls. We usually end up having very dependent p-values. Here I'm saying something very strong, that my null WJs are independently plus or minus 1 with probability of half. And I'm going to get this no matter what the distribution of y given x is, no matter what the distribution of x is, and no matter how I measure variable importance, including in arbitrarily complicated nonlinear ways. And that really comes from the symmetry that comes from constructing knockoffs. And that's like the magic. And I think, for me at least, once I have the coin flipping property, if I tell you that I have this, yeah, OK, maybe I don't totally understand this procedure in step 3, but I sort of believe that there exists a procedure that can take these WJs and control the false discovery rate, because this is like the nicest kind of statistical sequence that I could possibly have. It has really nice properties. All right. So one last picture for intuition before I go into the steps. This is a picture of, so I have variable importance on the y-axis here, and I have 500 variables and 500 knockoffs in red, blue and red. And you'll see that I have little gray dots here and blue dots and red dots. So the gray dots are the non-null variables in this case. And what we're going to focus on is the null variables, because if I want to control a type 1 error rate, what I need is something about the null distribution of these variable importance measures. And so, OK, I look at this, right, and I could imagine that if I saw these, if my variable importance measures followed, say, like a chi-squared distribution, right? If I knew that the distribution here, I could think of it as like popping out from the z-axis. If the distribution vertically here was chi-squared, just sort of fits, right? It's got more mass here. It's got sort of a tail here. If it were chi-squared, I would know exactly where to cut off to control some sort of type 1 error. But the problem is that these things come from this. I think the simulation used random forest variable importance measures. They have no statistical properties whatsoever. But they might do a good job of measuring variable importance. And so I don't know where to cut off. And indeed, if we imagine the case where we don't have knockoff, so if we ignore those red points for a second, I don't know how I would choose a sort of a threshold. And we can see that if I cut off at maybe 1.7 or so, if people can see the gray points, we get like 1, 2, 3, 4, 5, 6, 7, 8 true discoveries and 2 false discoveries. So,
Sorry, can I just clarify this? The
please.
colored points are the knockoffs. Is that what the null means?
No, red are knockoffs.
Okay.
And blue and red are nulls, right? So some of the original variables are null too, right? Most of the variables are probably unimportant in most problems, right? So my blues are...
Anything colored is a knockoff.
No, anything colored is null.
Anything colored is oh, sorry, okay.
Yeah. Anything
red is a...
Anything red is a knockoff. And in fact, technically, these are the knockoffs corresponding to null variables, because I also colored the knockoffs corresponding to not null variables in gray, but don't worry about that too much. And the important point is that, OK, I don't know the null distribution of these blue points, so I don't know where to set a cutoff. But what I know from the knockoff theory is that the null distribution of these red points looks the same. And so I can use this basically as a proxy for this. And indeed, visually, we can see this, right? The blue points and the red points, they look the same distribution. And indeed, they are. They're provably the same in a very precise way. And that's what's going to allow us to sort of set that cutoff that we need to know.
So the distribution of the knockoffs gives you an empirical null in some sense.
In some sense. In some technically incorrect, but intuitively correct sense, yeah. We don't actually use it as an empirical null. We're going to do something a little more precise, because the thing is that these are not independent.
Right.
So I'm not actually going to use this to set a cutoff on these.
Right.
I'm going to do something a little more complicated, but the idea there is very much. This picture definitely does, I think, tell you why knockoffs works, even though that's not exactly what I do. Yeah, question?
So you have 500 pairs of variables here,
Mhm.
right? Either one goes with 501, and they're both
Yep.
either colored or both gray.
That's right. Yeah, exactly. And so we think that the WJs, those knockoff statistics, would be the difference between the 1 and the 501 here. And since they're sort of equally distributed, what you should be able to see then, or imagine at least, is that their difference is basically symmetrically distributed. And indeed, that's what we want. That's what the coin flipping property is, right? It says that conditionally absolute value, the sign is a coin flip, and that's exactly what a symmetrically distributed random variable has. And that's what we're going to get, and I'll prove that later.
So null is synonymous with unimportant here?
Yep.
Okay, just checking.
Yep, that's my null hypothesis is the variable is unimportant. My alternative is that the variable is important. Okay. Yep.
So unimportant according to a threshold in W, or?
Nope, unimportant
In Z?
in theory, right? In the true model for y given x, I wrote down those H0Js. That's my null. It means that y actually does depend on that thing. That's my alternative. There's no the W's. Thresholding the W's is only that's how I get S hat.
Conditionally on all the
It's
other.
just confusing because you also have this definition of importance that's being given by the user, which is like totally.
Yes, that is confusing. Sorry.
Terminology is a little confusing.
This is like the ground truth.
Yeah. Yes.
Yeah, that's pretty bad notation. Sorry about that. No one's ever pointed that out to me before. I've only given this talk like 20 times, so that's a really good point. I hope not too many other people who've listened to this talk have been confused by that. But you're absolutely right. Important variables I'm defining under the true model, but variable importance I'm defining in a purely data-driven way, and that's really poor choice of words. I'm sorry about that. I'm probably not going to try and change it right now, but it's an excellent point. Is anyone still confused by that? Because that would be totally understandable.
Can I just say,
Yes.
so a clarifying question is really your alternative hypothesis is that a variable should be in the Markov blanket?
Yep, that's exactly it.
So to clarify that last point is, so if we were in a regime where we chose your ZJs so that they had nothing to do with the relationship between x's and y's, would that affect the size of the S hat? So
Nope. Oh, it would affect the size of the S hat. Absolutely, yeah.
Find anything.
That's right. Yeah. So if you have bad measure of variable importance,
ZJ will affect how many variables will actually come.
exactly.
Your power, I guess.
Yep, exactly. It's your power. Yeah. So if you have very bad measure of variable importance, like a uniform random number that has nothing to do with your data, you're not going to see any power. But you're still going to control false discovery rate.
I want to propose the
Yeah.
property about the symmetry of the sign. That's something that I'm a little confused about whether that's something that I have to make sure is true if I'm the one who gives you, no, that's something you're going
Nope. I'm going to give you. Yeah. You give me data and an algorithm for computing ZJ. I give you symmetrically distributed W's under the null. Yeah. All right. Step one. How do we construct these knockoffs? So this is my definition of knockoffs. This is what I need. So my X tildes, so these are my columns of my original data matrix, and my X tildes are my knockoffs. And I've colored things to make it a little easier to follow. So red is my knockoff, and this is what I need. So this is a very strong property. I call it swap exchangeability. So the full joint distribution of these 2p, n by 2p matrix stays the same when I swap the jth original and knockoff variable. And this has to hold for any j, and in fact, then this implies that if I swap any subset of the variables, also the distribution doesn't change. So this is the property I want. We can see that this is a pretty strong connection between x and x tilde. It says that they're definitely very similar in a very strict way. But it's not immediately obvious exactly what it's doing, so let me give you an example. The other thing, of course, is that we want the x tildes to be null. But all that means is just when I construct x tilde, don't look at y, right? If I were to construct them based on y, that would just be a bad thing to do because then they would actually be maybe non-null. And I just want to construct them only looking at x, and then I have this property automatically. So this is trivial, but it's certainly important, and that's what makes them knockoffs is that they're all null variables. All right, so here's my example. Suppose my x's are multivariate Gaussian. So this is a mean zero, and covariance is a p by p positive definite matrix. Then this condition is implied by having a covariance between the x1 through xp and x1 tilde through xp tilde equal to this. And so let's parse this a little. So of course we have sigma in this block, because that's just the covariance of the x's. It makes sense that I have sigma in the bottom block, that the x tildes need to have the same covariance as the x's. And it turns out that we need to have sigma everywhere in the off-diagonal blocks as well, except for on the diagonal of those off-diagonal blocks. And that's because I need that not only does x1 and x1 tilde have the same distribution, I need that when I swap x1 and x1 tilde, x1 tilde and x2 have the same joint distribution as x1 and x2. And that's exactly what the off-diagonal entries in this off-diagonal block represent. And so those all need to be the same as sigma as well. The one thing I can change is the diagonal entries of the off-diagonal blocks. And of course, if I didn't subtract something here, this would just be saying that x1 through xp tilde are exactly identical to x1 through xp.
So that's saying that x1 and x1 tilde can have any correlation you like.
Well, except that this, of course, needs to be a positive semi-definite matrix because it's a covariance. Yes, so indeed, so what do we want? We want our x's and our x tildes to be as different as possible because I want to be able to distinguish them if they're the same. My variable importance will all be the same and I'll have no differences. And then, of course, I need this to be positive semi-definite, so let's write that down in an optimization problem, right? This is how I would get my S. So I would minimize these. So these are just the covariances between x1 and x1 tilde, right? S, little s? Little s is something I defined just now, right here.
They're the elements of the diagonal.
It's a vector. Little s is a vector of dimension p, and I am about to find it, like this is how I'm going to find it, yeah. So yeah, maybe I should have said this expression for any s, little s, such that this is positive semi-definite, will give me a valid knockoffs, will satisfy this property. And then, okay, how am I actually going to find a good s? I'm going to do that this way. And what I'm saying is I want x and x tilde to be as uncorrelated, as small covariance as possible. I'm going to minimize the sum of the covariances. And then I'm going to set these constraints that basically make this a positive definite covariance. It's not immediately obvious. I probably should have written this differently, but this is equivalent actually to this thing being positive semi-definite. And it turns out that this is a convex problem. It's a semi-definite program, so I can solve this reasonably efficiently. There are things I can do to speed it up by separating my variables into blocks and then doing a correction factor so that I still get exact knockoffs, but can make this basically linear in P.
So what makes these good, like you said?
What makes these good is that the x and the x tildes are fairly different. We want them to be as different as possible.
Right.
And that's what's going to allow us to distinguish between them. What makes, and then I can measure that in terms of power. I'm going to show simulations later, but I'll see that will give me good power.
So this is in the same sense as like, even if you don't quite do it this well, you'll still control FDR, but it won't be powerful.
That's correct, yes. And there are going to be cases where it's impossible to do this well. For instance, when you have really, really highly correlated variables. And we'll see that because x1 and x2, if they are 99.9% correlated, then, okay, these two need to be 99.9% correlated, but also this one needs to be 99% correlated with x2, which means that since this is 99.9% correlated with x1, this and this need to be 99.8% correlated, which means that x1 and x2 are almost identical. And that's actually exactly where that no power to distinguish between them comes in when we do knockoffs. And there's nothing we can do about that, but that's not a knockoffs problem, right? That's a data problem. We really don't have the information in the data to distinguish those, and that problem goes away when we do group knockoffs. We remove that constraint and only require this exchangeability blockwise. Yeah?
So this construction makes sense if you have some multivariate normal data, but otherwise, just getting this covariance term is going to satisfy.
Indeed. Good point. So much more generally, beyond multivariate Gaussian, any distribution can have valid knockoffs. So this is a statistical statement, not a computational statement. So this is an algorithm, quote unquote. It's a procedure that, at least in principle, all of these conditional distributions are well defined. And I could, in principle, sample from all these conditional distributions, and that would give me an x tilde j that is a valid and non-trivial knockoff matrix. And I say non-trivial because, of course, I can always pick x tilde equal to x, but this is useless, right? So I want to get an x tilde that satisfies that swap exchangeability property, that is not equal to x, so that I actually have some power. And so this would do it. This is where, I mentioned there are going to be some assumptions. This is where you can kind of see where those assumptions come in. I need to know something about the distribution of x in order to be able to sample from these conditional distributions. And indeed, and at least in the original paper, what we assume is that we know x's distribution, the joint distribution of x, exactly. Right? So here, right, I'm assuming I know the joint distribution of x exactly. Then I need to know sigma then exactly. And then I can plug into this and get my s. And of course, once I have s, I can just generate my x tildes from the conditional distribution of x in this joint distribution. Okay, so this just says that at least in principle, we can do this for any distribution x. But computationally, that does not mean we can do it. And so there's been a lot of work recently in figuring out how to do this for various different x distributions. So we've got multivariate Gaussian I just mentioned. This is my paper. Discrete Markov chains was a paper very soon after, and hidden Markov models. This was really important for the GWAS application. That was one of the original motivations, because this is what people use for imputation. And so I think this made for a really satisfying application to GWAS, because we were actually using the same model that biologists use to impute missing data in GWAS. And that was the only assumption we were making, just assuming that we knew that about x. And that came from a lot of biology, right? We know a lot about that distribution of x. We input that into our method, and that's the only assumption we make. Everything else, we assume nothing about y given x, all those things. Gaussian mixture models have been done very recently. And then a much more general class of algorithms is what me and Wenshuo are actually working on right now. This paper should be coming out pretty soon. And basically, this should allow us, as long as there's some graphical model structure in the x's, so there's some conditional independence between x's and other x's, we have an algorithm that basically for any density gives us a pretty efficient way of generating knockoffs. Go ahead, please.
I'm sorry, I'm still ignorant, but what is the L? What is that? I don't know.
Law, it's a good question. I was sort of breezing over this. This is the conditional law of xj given these other. It's just the distribution, the conditional distribution. Yeah. No, the distribution. Law is distribution, yeah.
And then it's the conditional independence of xj that makes sure that those are null?
No, the nullity has to do with y, right? There's no y in here.
Okay.
The conditional independence is really just a greedy way of making xj and xj tilde as different as possible, given the other ones.
Okay.
Does it also help with the sign, or no?
The sign thing is guaranteed by just the fact that this is valid knockoffs, right? This is an algorithm for generating valid knockoffs. So this, I'm not sure what you mean by help with the sign thing.
I'm saying
You don't need conditional independence. In fact, we can show a more general version of this where you need some sort of conditional exchangeability, but you need a little bit more than that. But yeah, basically, yeah. I mean, you need some sort of exchangeability. It's actually not totally trivial to prove that this does produce valid knockoffs. It's sort of clear that at the jth step, it produces a valid knockoff for xj, right? Because they're conditionally independent given all the others. So okay, clearly that's a valid knockoff. But making sure that actually all the previous ones are still valid knockoffs is not totally trivial. And we can prove it, of course, but it shouldn't be obvious to you. It's just my point.
And is there anything that you can say if your model for x is wrong?
I'm glad you asked. That is also basically my next slide. Okay, so these are approximate knockoff constructions. So if you have a wrong model for x, or you don't know your model for x, there are some things you can try at least. So second order knockoffs basically just refers to what I did on the previous slide, where I fit the second moments, basically, to have this pairwise exchangeability property, the swap exchangeability property. Now, these don't come with theoretical guarantees, and that we can do like deep learning or GANs ideas. A whole bunch of people have happily applied those methods to generating knockoffs, and they seem to have some good empirical results, although you kind of need low dimensions because you need a lot of samples to sort of estimate the distribution of x. So it's not clear whether these are going to work in high dimensions. Second order knockoff seems to work fairly well in high dimensions as well, as long as somehow your variable importance measure only kind of depends on second moments. So if you're doing like random forests, which is like highly nonlinear, maybe it's not going to work so well. But if you're doing like a lasso, you're only really looking at like y transpose x and x transpose x, and so things aren't so bad. So these are approximations. They're things you can try in 2 slides. I'm going to talk about robustness. So when you apply an exact knockoff construction, but to a distribution that's actually wrong. So if you can hold on for that 1 second, I want to address one other thing, which is like, why all the fuss? So I gave this very precise definition of knockoffs. But the intuition, I think, a lot of people would say, well, okay, I could construct fake variables in a lot of ways. It doesn't require all this math and all this knowing the distribution. And if we remember this picture, basically this is what we need, right? We need these red points to look like these blue points. And so now I'm going to show you the same picture where I construct knockoffs. They're not actually knockoffs by my definition, in other natural ways. So the first one is, suppose I just knew the mean and variance of my x's, and I just generate IID Gaussian as my knockoffs. So we can see that the blue and the red points look super different here. That's the message, really, is that generating IID Gaussians, these do not satisfy what we need. They're not going to work as valid controls. And you can see that it's not even approximately going to give us what we want, right? If we look at a cutoff of 1, right, we can see 20 or 30 blue points above that line and 0 of the red points above that line, right? It's like nowhere close. All right, the next thing you might try is, well, okay, IID Gaussians, they don't match even the marginal joint structure of the x's. So why don't we do something that does? And this is totally model-free. We can just take x tilde to be a permutation of the rows of x, right? This seems like a natural thing to try. Unfortunately, it has the same problem. And this is really that point that even if x's distribution and x tilde's distribution are marginally the same, they are still, oh God, is that the time?
That's the real time.
That's the real slide number, so.
We have the discussion.
Good. All right, lots of great questions. I think even if there weren't questions, I probably would not be doing great. But it's important that I explain the intuition, and that I've mostly gotten through. OK, so this doesn't work.
Wait, why didn't they have the spiky ones there too?
Yeah.
What spiky ones?
Well, why are the red ones so depressed?
Because basically these nulls might be correlated with some real variables. And that's why some of them are spikes. And the problem is that because these are permutations of this, none of these are correlated with real variables. They're correlated with knockoffs of real variables, but none of these are real variables, and that's the problem. And that's why we need the swap exchangeability, not just that the marginal distributions are the same.
Cool.
And so this really doesn't work either. OK, this is robustness. How should I use my last 10 minutes? I am going to go through this very quickly. OK, this is the picture I'm showing you. This is basically error in the x distribution that you think you have. It's not your real x distribution. It's close. So this is saying I have the exact x distribution. I do knockoff, so we know that this works. I have exact false discovery rate control and high power. And what we see is that as we do worse and worse, what might surprise you is that instead of this going like this, right, I don't lose FDR control. I actually end up getting lower FDR. What I end up finding is that as I have to basically learn more and more from the x's in my data, I actually end up overfitting my data more and more because that's the only information I have. What ends up happening is I actually become conservative. I think this is actually kind of desirable from a scientific standpoint. It says that if I really don't have enough information to run this procedure properly, I don't end up thinking that I magically discovered something amazing that I didn't. I'm just going to say, oh, I can't discover anything. Right? So the power goes away, the false discovery rate goes away. This is really different from what you would normally see in a plot like this, where if we have overfitting, the more and more we overfit, usually, right, we really lose type 1 error rate control. We're going to make more and more false discoveries, and that's actually not the case here. This is just an empirical example. This is something we'd like to understand better theoretically. But I want to get to step 2 at least, because this is really at the heart of, I think, what makes knockoffs so exciting. All right, so remember that we had these variable importance measures, 1 through p, and z tilde 1 through p. So these are the variable importances for x. These are the variable importances for the knockoffs. And these are computed again, however you like. And then I'm going to pick some anti-symmetric function. That just means it takes 2 variables, spits out a scalar. And when I swap the 2 variables, I get a minus sign. So for instance, a minus b. Perfect good anti-symmetric function, the one we actually always use. And then I'm going to set wj to be fj of zj tilde. So this is, again, measuring the relative variable importance between xj and its knockoff. As an example, z could be some sort of fitted coefficient from a lasso regression. I take a minus b, and I get this, what we call the lasso coefficient difference statistic. As another example, we could take a machine learning method, fit to y and xx tilde, and the cross-validated drop in, or I guess increase in error when you drop a variable. That's going to be our measure of importance. So that looks like the cross-validation when I drop the jth variable minus cross-validation with all of them. And the same thing when I drop the jth knockoff variable. You'll see that the CVs cancel out, and we just get this. I don't have a name for it, but it's a measure of variable importance you could use. I think it's a reasonable one if you think you have a really good machine learning method. And OK, I think this is a really important slide, is that you can do a lot with these z's to try and use what information you have about your data to give you better power, right? Your choice of z is really a question of power. I'm guaranteeing you with knockoffs that I'm going to control the type 1 error. It's your job to pick a good z to have good power. And basically, I'm going to give you a lot of freedom to do that. So z can really be anything. One of the cool things we can do is be super adaptive. So I could say, I don't know if a random forest is going to fit well or whether a lasso is going to fit well. Maybe I think if my fy given x is really bumpy, a random forest might fit well. It's sort of nonlinear. But if it's approximately linear, I think a lasso, a L1 penalized regression is going to work well. I can try both. I can look at the cross-validation error and pick the one with lower cross-validation error, use that to derive my variable importance measure. That's a totally valid statistic. I can be totally adaptive to my data in that way. In fact, I can even take it a step farther. I can even, if you tell me the distribution of x, I can generate knockoffs, and then I can give you y and the pairs xj, xj tilde unordered. So I'm going to give you a random swapping of them. So you know what all the x's and x tildes are. You just don't know for the jth variable which one is x and which one is x tilde. If I give you that, you can do whatever you want. Literally anything to compute z, and then you just give me back z, and that is going to give me FDR control. So I don't even need to know what you did. You don't have to tell me anything, but I have constrained your information in just a little bit by masking which one is xj and xj tilde, and you can do anything you want, and that's going to give you exact FDR control. All right, on the other sort of end of the spectrum, if you know a lot, you can take, say, a Bayesian approach, where you choose a prior in a model, you use some sort of posterior probability that xj contributes, and then we still give you good FDR control, even if your prior is wrong, or even if your computational method hasn't converged, all the guarantees still hold. But to the extent that your prior is sort of gives you good information, and your computation works, you're going to have high power. This is my slide for proving that it works. I'm going to skip this. And skip this. This is what I do with the W's. This is why that's a good FDR hat. And show you some numerical results. OK, so model X knockoffs, the method I'm talking about. This is sort of the old knockoffs. This is Benjamini-Hochberg on maximum likelihood p-values, because it's a low-dimensional linear model, so I can actually compute those t-statistic p-values that Wenshuo mentioned. And these are marginal p-values, which in this case are actually valid because all of my x's are independent. Not a very realistic situation, but it's sort of a best case for all the competing methods so that we can actually compare our method with those others. And what we see is that model X knockoffs is actually more powerful than those. We have the same message here, except that now when you do maximum likelihood p-values in a logistic regression, and that's what this is, they don't work. This is what I was saying, is that it's really hard to get p-values, even in low-dimensional nonlinear models, that the maximum likelihood p-values for logistic regression, unless n is much, much greater than p, are totally wrong. And here n is definitely, n is 3 times p, and still the p-values are nowhere close. And that's why we don't have FDR control for the green curve, because those p-values are actually invalid. And those are the p-values that R spits out, right? Totally default. You should not trust those p-values unless n is a lot bigger than p. 3 times is definitely not enough. All right, these are more simulations. I want to get to this. So at least I want to talk about computation for 5 minutes. We analyze this data set. Computationally, this is not so hard to do. When we analyze this data set, we used what, given the algorithms that exist now, we used basically the slowest algorithm for generating knockoffs, and still this was pretty fast. When we parallelized it over a bunch of machines, it basically took an hour to do this whole analysis from start to finish. As I mentioned, we make twice as many discoveries. It seems like the new things we discovered actually are at least promising. They're not totally made up. And although in this analysis, in the paper I wrote, we use a multivariate Gaussian approximate model for x, clearly wrong since the SNPs are 0, 1, 2 valued. When this follow-up paper solved knockoffs for hidden Markov models, they did the same analysis on the same data with the much better model, and actually got basically the same answer, which again speaks to sort of the robustness of knockoffs of doing what we want. So there.
Using the HMM to model the correlation structure of the SNPs.
Exactly. Yeah. Or to model the whole distribution, not just the correlation, but everything, right?
Yeah.
So there are Python and MATLAB packages for, but unfortunately there aren't all of them for every single construction of knockoffs. But if you have a type of construction of knockoffs that you want to do, and you don't have, and it's not in the language you want, please let me know, and we'll figure out a way to make it work. They generally scale basically linear in P and N, so that's nice, right? Can't do too much better than that. And basically all the computation then comes in computing these variable importances. And so, we have to compute variable importances for twice as many variables. So if you had to run some complicated machine learning method, now you have to run it on twice as many variables. So basically that's going to add some constant order factor to your computation time. Ideally you wouldn't have that, but it's not going to change the computational complexity. It's just going to add a constant, right? And then since I'm out of time, I'm going to skip this and just go to the summary. So I told you about this method. Hopefully I gave you some intuition about why it should work well. And it does work well. We have exact guarantees on the false discovery rate. And basically, I'm very interested in making knockoffs work for you. That's why I'm talking at the Broad, is I would love to hear about the problems that you have that are variable selection related. It doesn't have to be exactly fit into this talk, but if you think it's something like that, I'm definitely interested in extending knockoffs to work in other settings as well. So if you think this could work for your research or help you do cool science, please let me know, and I would like to help you. That's it. Thanks.